All right. So at this point, take a moment and think about everything you've actually learned this semester so far. Raise your hand if you've never programmed before showing up to 161. Okay? Now you know how to write code, write functions, loops, ifs, booleans, different types, variables. You know how to make objects. You know what lists are, which are a big thing. You know a lot. Realize, like, whether you like it or not, you know a lot. You've learned so much. And if you consider that, 2.5 months ago, you knew nothing about this. So first semester computer science is always a heavy course. It doesn't mean it's hard, but it's not trivial, that's for sure, as you could probably tell. Because there's so much you got to learn before we can actually teach you any computer science. All the stuff you've seen so far, yeah, it's computer science, but it's as much computer science as picking up a pencil and writing is English. You know, like it's a part of the process. But there's so much we get to go into in computer science that's well beyond writing code. That doesn't mean that writing code isn't important. No, it's a lot of the foundation of everything you're going to do in computer science. You got to write code to do stuff. But it is not, there's so much more. So you've learned a lot, and it's getting to the point where you can finally start learning the good stuff. Again, not to say that any of the stuff we have learned so far isn't really awesome. It is. But this is where things start to really get interesting. So we've actually gone pretty deep into the topics. So it's time to go back to some basic CS stuff. We talked about objects. That's pretty big. We've talked about, like, everything in the course we've done. Like, we went deep and explained, we got through and saw what all of those tools are that you got in your tool belt. You've got a very well-equipped tool belt at this stage. In terms of the fundamentals, you got it all. All of those things, like your types, your variables, the values, the functions, the loops, the if statements, objects, those are all the big core things. Everything else on top of it is just building on top of these core principles and ideas. So at this point, we have a lot of tools in our tool belt. We have a solid understanding of some data structures. Most importantly, it's the list. That's the one that we really, really care about. Sure, we also looked at sets and dictionaries, which are also really important. Dictionaries, tuples, NumPy arrays, but really the big one at this point is lists. But we've missed out on, like, the algorithms. All the code you've written, they're algorithms, they are. But we're now getting to the stage where the emphasis really is on the algorithm idea and not the code. So to bring this back to linear search, which you're all experts on at this point, what is the linear search? Well, we can look at the linear search code. Let's go look right here. Here's Python linear search. This is just checking if something exists. It takes a list and a thing. For each index in the list, if the list at that index is the thing I'm looking for, we found it. Otherwise, keep going. I mean, that's the code there. But try to think of these steps as not code. Think of these steps as just a series of instructions, because I can explain to you this algorithm without mentioning Python or any code. If I gave you a stack of exams and told you, find the exam with the name Bob on it, and you say, well, how do I do that? Well, I start at the beginning, you look at each of them until you find the one you're looking for. If you don't find it, I guess it's not it. Right? That's the algorithm. Then we wrote the algorithm in the language that the computer's happy with, like Python. But the core idea here, the algorithm itself, is what's interesting. It's the important basis of what the code is. The code is just an expression of an algorithm. They are not the same. So keep these ideas separate. And if we go, we've talked about this a lot already. If I have a list of n elements, how many do I need to look at to guarantee I will find the thing I'm looking for in the list or conclude that it must not be in that list? How many things must I look at? N of them, all of them. Because if I'm looking through that pile of exams, they're not sorted or anything, and I get to the second last one, okay, and I look at it, it's not it. Now I've got the last one, but I haven't looked at it yet, and I'm looking for Bob. Can I yet conclude if Bob is in that pile? No, I have to look at that last one. I still don't know. Sure, it might feel like, well, it's not likely if you didn't find it so far, but I mean, you don't know. You need to look at them all before you can make any conclusion. So, when we start talking about the algorithm, again, linear search, your first real algorithm. I was talking about this before. We like to geek out about these algorithms. Like, okay, what does it mean? Is it correct? Like, can we convince ourselves that it's correct? How many steps is it going to take to run? Can we find a better algorithm to do the same thing? Or a different algorithm to do the same thing? What does it mean for an algorithm to be better than another one? These are all the questions we start to really care about. So at this stage, linear search. You start at the beginning, you look at each of them. If there's n things in that list, I gotta look at all of them in order to conclude whether or not the thing's in there. If I double n, I have to do twice as much work. If I multiply n by a factor of 10, so I have 10 times the number of things in the list, I gotta do 10 times the amount of work. As n gets bigger, as that list gets bigger, the total amount of work I have to do grows the same way that the list grows. Every time I add a new thing, I've got one more step to do. If I double it, I got twice as many steps to do. It just grows at the same rate. If I plot this, it would look like a straight line, right? X equals y, effectively. You know, that line, 1, 1, 2, 2, 3, 3, and so on. That's the total amount of work happening in this linear search. What's the best case scenario, though? I've got some arbitrary list. Best case scenario, what would be the configuration of that list to have the best case scenario? What do you think? Like minimal amount of computing required. This is not a trick question. Or maybe it feels like it is because it's so easy, but. So who said that? Bingo. You find it at the beginning. I'm looking for Bob. Bob. Done. How many things do I need to look at? 1. Best case scenario, it's 1. I could have a list of size bajillion. And if I find it in the first spot, great. Worst case scenario, it's at the end or not even in there. I have to look at them all. On average, if you kind of think, on average, how many steps? Let's say you did this linear search a billion times. Lists of who cares how big the lists are. I do a linear search for Bob in this list of things. Then I go through it. Then I look for Bob again in another list of things. And then Bob again in another list of things. Maybe it's the same list that they get shuffled out. On average, how many things will I be looking at? It'd be like half of n, right? Because you'd figure, for every time it's in the first spot, it's in the last spot. For every time it's in the second spot, it's in the second last spot, and so on. So if you kind of kept track of the number of steps every time, it's probably going to be like half. On average, it'd be like half of n. On average, a linear search will take half of n. Now, we're going to get it way more into this next semester. But a funny thing is when we talk about half of n, I mean, half of n is clearly better than n, right? But in reality, the computer scientists, because we are so concerned with not so much the total amount of work being done, but how the total amount of work being done changes as n changes. So it's not just like, oh, okay, n, we got to do half of n work, that's better. No, really what we care about is how much more work do I have to do as n grows. And because of that, something like 1/2 of n really isn't that much better than n. Because what I want, so you'd be like, well, yeah, no, clearly it is. Obviously, half the amount of work. Well, you're right. But we start talking about like orders of magnitude difference in things. Because if something grows at the rate of n squared, and there are algorithms that we will see in a couple of weeks. Well, I guess this is the second last week, probably next week. When do we talk about sorting? Okay, next topic. We will look at some n squared algorithms where as n increases, the total amount of work increases at a rate of n squared, which is way faster than n, or half of n. Yeah?
So that means you have to create algorithms that are exponential?
Well, we don't want exponential algorithms if we don't have to, because we want it to require less and less work.
No, I get that. I was just thinking in my head, thinking, wouldn't that be exponential? I'm probably completely wrong.
Say that, wouldn't that be what?
I was thinking in my head that would be exponential.
Which would? The n squared?
Yeah.
Well, here I can do a quick. I don't know if this is going to crash. If we have something that grows linearly, it's going to look something like this, right? And if we have something growing half linear, it will look something like, I don't know, not quite that steep. Pretend I'm good at this. But if we had something that's going to grow at the rate of n squared, it's going to grow, let me change the color. If I can find the color. If something grows n squared, it's going to grow like this, right? Perhaps not quite that steep. But it's going to grow so much faster that the difference between the growth of n and the growth of n and half of n is so little compared to the difference between n and n squared. Because let's say, for example, we have n. If n is 1,000,000, and we are doing something that's going to grow linearly, well, I've got 1,000,000 steps to do. If n is 1,000,000 and it's growing at the rate of half n, like the total amount of work going to be done on average is half n, okay, fine, 500,000. But if this is 1,000,000 times 1,000,000, oh, we got 1,000,000 millions. That's a lot. We have 1 times 10 to the 12. So if the size of the list is 1,000,000, the difference between something that's n and half n is 500,000. The difference between something that's n and n squared is insane. It's 1,000,000 times worse. And that only gets worse and worse and worse as n gets bigger and bigger and bigger. And again, it's as those values grow, how does it change? So you might say, well, n is clearly worse than half n. You're right. But at the end of the day, those algorithms are going to be far more similar than something that grows like that n squared. Any questions about that? Don't worry, this stuff is not on the exam type thing. It's just, I want you to get the intuition. That's what's important here. Next semester, we'll geek out about this a lot more. All right. So, all right, no, already did that. Cool. Can anyone think, okay, so I'm searching a collection of things for a specific thing. And it seems reasonable that, well, in order to check if something's in there, we could probably, we're probably stuck doing a linear search, right? And I know we looked at dictionaries, but dictionaries have to be set up beforehand. If we just have an arbitrary list, and you want to check if something exists in there, you know that you got to look at everything in order to conclude whether or not it's there. Can anyone think of a better way to do it? You're stuck with a list. You can't use the dictionary or a set. Take a moment, talk amongst yourselves. Can you think of a better way to do this search? Can you do it in a way that doesn't grow like n? That doesn't grow linearly? That if you double the input size, it's not twice as much work? Can anyone think of a... Take a moment, talk amongst yourselves, see if you can figure it out. Does anyone have any ideas? Any ideas? Okay, here's what we're going to do. I need a volunteer. Let me first explain what the trick is going to be here. So, I'm going to ask someone to pick a number between 0 and 1023. And I will guess your number. I will find your number in no more than 10 guesses. Not 1,024 guesses. 0 to 1023, zeros included. So I will get it in 10 or less guesses. Not n guesses. I'm going to get it in less than 10. 10 or less. So it might be 10 guesses. Who's going to be the volunteer? I want to see if I get, not one of the usual. Let's go with you. Okay, don't tell me the number. Think of a number between 0 and 1023. Okay? All right. Okay, you've got it in your head, right? Okay, there's one catch. I'm going to ask you higher or lower, and you got to tell me. Will you give me that? Sure. Okay, cool. All right, here's my first guess. 511. Lower. So that's one guess. 255. Lower. 127. Lower. 63. Lower. 31. 15. 23. 27. 25. I wonder what it's going to be. 26. Oh, I got it in 10 guesses. Thank you. Yeah. How about I guess the number between 0 and, wait, 1, 2, 3, 1,450,000. 48,575. 0 between 1,048,575. I will get it in no more than 20 guesses. Who wants to do this one? All right, you've got a number between 0 and 1,400,000 and whatever. Okay, it's there. Tell your buddy so we know you're not cheating. All right? If you think you're going to trick me. Okay, are you ready? Again, you got to just tell me higher or lower, okay? Okay, 524,287.
Lower.
262,143.
Lower.
You just pick 0 or something. Okay. That doesn't count as a guess. 131,071.
Lower.
65,535.
Lower.
32,767.
Lower.
16,383.
Lower.
8,191.
Lower.
4,095.
Lower.
2,047.
Lower.
1,023.
Lower.
First of all, I'd like you to notice an interesting thing. That was my 10th guess. And look at the number it was. 10,023. Interesting. Right? Raise your hand if you're like, oh yeah, that is cool. Raise your hand if you have no idea why that's interesting. It's because last time I told you to guess a number between 0 and 1,023, and I said I'd do it in 10 guesses. I've got 10 guesses left. All right. All right. Was it, wait, 1023? You said lower?
Yeah.
511.
Lower.
255.
Lower.
127.
Lower.
63.
Higher.
Oh! 95.
Lower.
79.
Lower.
71.
Lower.
67.
Higher. Going too low.
69.
Correct.
Correct? Nice. 19 guesses. Wow. So, raise your hand if you saw the pattern. Who here knows what a phone book is? If you are looking for the letter, I don't know, M, and you open up that phone book, and you're currently looking at the letter J, okay? So you're looking at the letter J. Everything over here, let's say you just happen to turn to the first page of the letter J. Everything over here comes before J, right? Because that's how alphabet works. Everything after this is J and further. Which side of the book do I go to? That one. Why? If I open up a big textbook with 2,000 pages and I'm looking for page 1,500 or something, sure, I might eyeball it, but how about this? How about I open it up to page 1,000? So I have pages 0 through 999 over here, and 1,000 to 2,000 over here. Where do I continue my search? On that half or that half? I go to that half. How many pages did I eliminate from my search? Half of them. So let's say I turn to let's say I'm looking for 1750, page 1750. So I go about halfway between 1,000 and 2,000, and I just happen to get to page 1,500 exactly. All the pages to the left now are between 0, or I guess really I could say 1,000 and 1,500, and then 1,500 to 2,000. Which side do I go to? That side, because I'm looking for 1750. How many of the remaining pages did I get rid of? I have 1,000 pages. 500, thank you. Which is about half, right? Every single time I made a guess, I threw away half the numbers. I started at 511. Then I went down to 255, 126, well, whatever it would have been. I just keep halving it. I'm going to do the number guess again. And I'm just going to say lower every time, as if I'm guessing, let's say it was the number 0. Just watch what happens to this number. It halved every time. Roughly halved every time, because sometimes there's like rounding, decimals, 0.5s. Do you see how I just kept halving it? Yeah.
Is there a reason that there's no even number?
There is an even number. It's just that if I set a guess number between 1 and 1024 instead of 0 and 1023, it just so happened that every time we halved the odd number, it had to get rounded down. That's why. It just happened because we started on an odd number and then half. That's why. So every time I made a guess, I was able to eliminate half of the remaining numbers, which is really cool. So n, then it was n over 2, then n over 4, n over 8, n over 16, n over 32, and so on and so on and so on. Does anyone know what the relationship between like n and the number of steps it took? So I had a total of 1,024 guesses the first time, and I got it in 10 or less, right? The next time it was, over 1 million, and I got it in less than 20 guesses. Any idea what the relationship between 10, 24, and 10 is? No one has any idea, really? What do you think?
Is it like 2 to the power of 10?
It's the opposite of that. It's the inverse of that. So 2 to the 10 is 1,024. What's the opposite of like the power of? Log. Except it's log base 2 in our case because we're halving every time. In computer science, we talk about log a lot, but it's almost exclusively base 2, which means it's easy. It's just half. So the relationship is the number, the size of the list, n, and the total number of steps I needed to take. Worst case scenario, the total number of steps I needed to take was log n. If I had 1024, it took me 10 guesses. If I did a linear search instead of this fancy one, how many guesses would it take me to guarantee I find it? All of them, n. But here I only needed 10. So if it was a linear search, I need to look at 1024. If it's binary, I only looked at 10. How about this? If I'm doing a linear search and I'm looking at 2,048 numbers, how many do I need to look at to guarantee I find it? In linear search. All 2,048. So I doubled the amount of work I needed to do. Linear search, I doubled the size of the list, I doubled the amount of work I needed to do. But with this fancy search, if I double the amount of work, how much more work do I need to do? Or pardon me, if I double the size of the list, how much more work do I need to do? I'll give you a hint. Any ideas? Just one more guess. And I'm guaranteed to find it. If I double it, it requires only one more guess. Which algorithm is going to require way less computing time? The linear or this fancy one? Yeah.
Wouldn't we need to know what it is for this?
Well, so I think I know what you're getting at. There is a giant catch to what I was doing, though, right? What was the catch?
We gave you the number, or we told you, less than or
Exactly.
or below and all that.
And that, at the end of the day, the data I had to be sorted. I needed to be able to go, do I look at this half or this half? So you needed to be able to tell me which way to go. So this search, what we call a binary search, binary 2, half, 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 half. This fancy search here, this binary search, which is way faster than a linear search, requires that the data is sorted. Which maybe it is, but in general it won't be. So we get a way better algorithm if we change how our data is configured. If the data is sorted, I can do this search so fast. If it's unsorted, I'm stuck with a linear search. But just by having the data sorted, we can come up with a way different algorithm that's way better. Is there any questions about that? Yeah. How would I go about sorting it? Funny you should ask. That's the next topic. And we will start talking about some sorting algorithms that are absolutely terrible, but they're the ones that we all do. Raise your hand if you've ever sorted anything before in your life. Put your hand up. Of course you have. You probably never really thought about the algorithm you were executing when sorting those things, right? You just sorted it. You just did stuff and then you ended up with a sorted list. Presumably if you were successful at sorting the thing. You somehow figured it out, you sorted it. And chances are, when we look at the sorting algorithms next topic, when we look at the sorting algorithms, you've probably done these algorithms one way or another without really realizing it. But like good computer scientists, we're going to geek out about something as simple as sorting, which sounds simple, but it's a problem that's easy to understand. We all know what sorting is, but it's non-trivial. So we love searching and sorting to start learning computer science because you all know what sorting is. So it's not this mystical problem I need to teach you. You know what the problem is. So it's a little easier for us to talk about solutions to the problem because we all understand the problem really well. And we're going to look at a variety of ways to sort things because there are a bunch of ways we can sort things, some better than the other. A lot of the sorting algorithms that we're going to see next topic are n squared, meaning that as n grows, the amount of work we have to do grows quadratically, which is pretty rough. There are better ones that we'll look at, and there are some really interesting, cool ones that require some special tricks, or maybe some concessions of sorts. For example, no, I'll save this for the next time. All right, so, and a linear search, yeah. Okay, yeah, we already did this. Okay, cool. So, remember, and I've probably shown you this already before, but I love talking about this because it helps emphasize that when you're writing the code, you're implementing an algorithm. I could speak multiple different languages, like natural human languages, and I can explain this algorithm to you in a variety of different languages, in the same way I can express it in a variety of different programming languages. The algorithm is the same. The code's a little different. But look, here I've got Python, C++, and if we scroll down just a bit, we can see Java as well. Look at those 3 chunks of code. Can you see it reasonably well at the back? Take a moment and look at that code. The top one, Python, you should be very familiar with. But I'm willing to bet that once you look at the C++ and Java ones, you'll realize that, okay, the syntax is a little different, but the algorithm's the same. You look at each thing in the list, check if it's the thing you're looking for. If it is, you're done. Return true. Otherwise, keep going. The algorithm is the same. In fact, it's so similar that, look, so in Python, this is a list, this is thing. For each thing in that list, is the thing at that index equal to the thing I'm looking for? Yes? Otherwise, keep going. Here, so this is the list in C++. We'll call it an array. And n, We can't ask the length of the array, okay? So I just have to pass it as a parameter. But for I to 0 to less than n, if a list at index I is the thing I'm looking for, return true. Otherwise, keep going, and then if you get to the end, return false. Java. In Java, I can ask the length of the list. Great. It's an array, we call it, but whatever. So we've got a list, the thing I'm looking for I from 0 to the length of the list. If it's the thing I'm looking for, return true, otherwise keep going. They're the same. The syntax is a little different. When people learn like, oh, we're switching programming language, I'm going to have to learn a whole new... There are syntax differences you'll have to deal with, but you'll see that a lot of these programming languages are very, 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 very similar. Especially once you get down to the basic tools, they're effectively identical. Sure, once you work up and build up in the languages, some things get different, but at the stages we're at, they're effectively the same, which is pretty cool. Now, if you want to see a programming language that's different, well, here's it. Here we go. And this is actually a beautiful algorithm. It's just, who here thinks it looks mostly like Egyptian hieroglyphics or something? Because, yeah, it totally does. But it's actually really interesting. But we'll talk about that one another time. So you'll see, like, this is what it means for a programming language to be, like, different. Really, it's not that different, but it's clearly more different than the other three. So don't panic. We're going from Python to Java for next semester. Java, the algorithm is the same. Remember how like on assignment 3 I gave you the pseudocode? I could have given you that pseudocode and told you to implement this in Java. The pseudocode would be the same. Because the pseudocode is just a description of the algorithm. It had nothing to do with Python. I gave you the pseudocode for the tic-tac-toe. And that pseudocode would have been just as applicable as if I had you do this in Java versus Python versus C++ versus something else. Because the algorithms are what's the same. It's the syntax where things get different. Any questions about any of that? Has anyone ever heard of Haskell before? No. It is not a widely common programming language, but it's kind of neat. And what's cool about Haskell is you're not allowed to use loops. There's no such thing as a for loop in Haskell. You can't do it. You have to do everything with recursion, which is interesting. But again, we'll talk about that a little bit later. Put your mask on. All right, so the next topic, sorting. So, okay, what's this warning? We're in the domain of non-trivial algorithms. You should not expect to look at these. Oh, yeah. There is zero expectation. In fact, there is a 100% expectation that when you look at the algorithms, it's not going to be immediately obvious. If it is, you're weird. If it is, and you're not a computer science, transfer to computer science immediately, because that means you're really good at this, and you'll be rich. So the algorithms we're going to look at, when you first look at them, you're not going to understand them immediately. They're complicated. You have to take your time to look at them. And the trick is, what does the code say? Interpret it. We'll take our time with it. So, there are a lot of ways to sort things. And I know you all have done it one way or another. Some algorithms are really bad. Like here's one. Imagine I had a deck of cards. You know, like when you open a deck of cards, they come in, like for the very first time, they're like ace, 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 2, 2, 2, 2, ace, 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 2, 2, 2, 2, and so on and so on and so on. There's a nice order to it. So let's say I take an old deck of cards, and I want to get them in that same sorted order. So here's a strategy I could go with. Take the deck of cards, and shuffle them, and check if they're sorted. And if it is, I'm done. If not, just shuffle it again and try again. Who here thinks that's a good idea? It's a terrible idea. I might be doing it forever. I mean, how long does it take If I have a list of size n, how long does it take to verify that that list is, in fact, in order? How many things do I need to look at? N. I gotta look at all of them. So best case scenario with that shuffling strategy, I can, maybe the first shuffle I get really lucky. Order n, done. That's awesome. But in general, that's not going to happen. So this strategy here, terrible search or sorting strategy. But you know, it's a very silly one, but maybe it'll work. If the size of your list is relatively small, like really small, like 8, yeah, that strategy could totally work. But once you get past that, yeah, it's gonna become terrible really quickly. Some sorting algorithms are pretty good. Some are terrible. Some are good in certain situations. Some have certain features that we like and other ones don't and whatnot. But there's a lot of different sorting algorithms. So take a couple minutes and talk amongst yourselves. Start by taking a minute and thinking about the last time you sorted something. Obviously, you don't remember. But if I gave you something to sort, think about how you would do it. Okay, think about the steps you would execute to start to end, unsorted to sorted. Think of the steps. What are the steps you would do as a human to sort a pile of exams alphabetically or something? Take a moment, think to yourself, and then talk amongst yourselves and compare ideas. I'm curious if people have similar strategies or not. All right, it's too quiet. Talk amongst yourselves. And if you're far away, go close to somebody. Okay, who's kind of thought of the way they've sorted stuff? Put your hand up really high, I want to see. So for those of you without your hand up, that means you just can't figure out how to sort things, eh? Uh-oh. You're going to have a really hard time in the exam. Not because you sort things, but because... So, okay, put your hand back up. Okay. All right. So who wants to tell me the general high-level idea of the sorting that they thought of? Or who wants to volunteer the person they talked to because they think that they had a really cool idea? Who are you volunteering?
Okay, yeah.
All right, what are you going to do?
I'd take the exams and I'd look at the first letter in the name, and I'd have like 26 piles. So then I'd put like, oh, that one goes in the A file, that one goes in that file. And then I would take the individual piles by letter, and then I would do the same thing with the second
Okay. So what you just described is actually a really awesome sorting algorithm that is distributed and non-comparative. That is really, really, really good. So you just ruined everything. But what you did is, sometimes what they'll do is they'll call what you did bucket sort. And the easiest thing to do is, by the way, if I'm ever sorting exams, that's exactly how I'm doing it. Except I'll stop after the first round because it's sorted enough. So I'll look at the first one. I'll have 26 bins. A, put it in the A pile. Z, put it in the Z pile. F, put it in the F pile. And just do it. And at the end, I just stack them all together. How long did that take me? If I had n things in my list of things to be sorted, how many things did I have to look at? All n of them. And sure, maybe you think like, well, yeah, but you had to look at each letter to find which one it went in. All right, fine. N times 26. N times k, where k is the number of things. But 26 is still nothing compared to like n, which like n can grow arbitrarily large. 26 is always 26, so it's like meaningless. So that's a really good sorting algorithm. What were you going to say? Yeah. All right, so everyone's thought of the best idea. So what are some other ideas for sorting things? Come on, someone's got to share what they were doing. I saw a lot more hands up. I'm going to point to someone. All right, what are you going to say?
I kind of said, like, if it's, like, I put one down on the table, if it's higher alphabetically, I put it, like, on the right side. If it's lower, I put it on the left side. Then with the next one, I compare it to all the ones already on the table.
Figure out where you put it? That's called insertion sort, actually. What were you going to say?
I was not going to say this, I just thought it was a point. You could just look for all of the A's and then make that out, like looking through the list instead of sorting them as you go. Like find all of the A's, put them down, and then find all of the B's, put them down.
I think that's what he was doing.
That's like super efficient.
No, I was like, I look at the first one, and if it was an A, I put an A.
Oh, so you're going through and finding all the A's.
Yeah.
Then you're going through finding all the B's. Well, that's actually very similar to something called selection sort. You're basically doing selection sort. Interesting. So insertion sort is you find a thing and you figure out where to put it in a sorted collection of things. Selection sort is going through and finding the smallest thing. Then go through and find the next smallest thing. And then the next smallest thing. And then the next smallest thing. Any other ideas? All right, we're out of time, but maybe we'll pick up here whenever we have class next.